Hey, everybody. It's Wednesday, May 5th. And as you can see here in the aim today, our goal for today's video is to review the two free response questions that were assigned yesterday. We've got two questions, and one of them is a 25-minute question, so I'm just going to get straight to it. This question, the first one, 12 points, 25 minutes, says, a long track inclined at an angle theta to the horizontal has small speed bumps on it. The bumps are evenly spaced to distance d apart, as shown in the figure above. The track is actually much longer than shown, with over 100 bumps. A cart of mass m is released from the top of the track. A student notices that after reaching the 40th bump, the cart's average speed between successive bumps no longer increases, reaching a maximum value v average. This means that the time interval taken to move from one bump to the next bump becomes constant. Now, I thought that part of this question was fairly generous. This means the time interval taken to move from one bump to the next bump becomes constant. Because you should realize, based on the description in this problem here, the distance between the bumps is fixed. It says it's a distance d. And if average speed is distance over time, and this is fixed, and now they're telling you eventually this thing is becoming constant, then that has to mean here that the time is going to be constant as well. And so that's the basic idea. This thing's average speed is staying the same after it gets to the 40th bump. Now, of course, that's particularly relevant to part A, 1, and 2, because it says here in part A, consider the cart's motion between bump 41 and 44. Keep in mind, this is the portion where that average speed is now constant. It says in the figure below, sketch a graph of the cart's velocity v as a function of time from the moment it reaches bump 41 until the moment it reaches bump 44. Over the same time interval, draw a dashed horizontal line at v equals v average. Label this line v average. I like this question because it's a kind of question that you've never seen before. They do dream up some totally bizarre situations on the AP test, but this is a good thing for us to talk about, I think. So I think the big question that we have to ask and answer here is what is the function of the bumps? What are these bumps doing to the car? And the bumps are going to be slowing down the cart. When the cart hits the bumps, it causes a sudden decrease in velocity. Now, you have to realize that even if you didn't totally understand that right off the jump, it should be noted in between the bumps. I'm just going to go back here. In between the bumps, the cart is traveling just down an inclined plane some distance. That means, roughly between these black lines, although I guess I could have drawn them a little closer to the bumps, this thing is still accelerating. And so we should see a constant acceleration between the bumps, because remember, on an inclined plane, the acceleration is g sine theta if there's no friction, right? Because FGX is going to be mg sine theta, and of course, if we want to find the acceleration, then we just take the force divided by the mass. So the mass is going to come out, and we're just going to get g sine theta. So we should see a nice, constant, smooth acceleration between the bumps, and then a sudden decrease in the velocity at the bumps. It's going to end up looking something like this. So at the bump, we're going to see this sharp decrease in the velocity. And then we're going to see an increase in the velocity. And then we're going to see sharp decrease once again, and then an increase in the velocity. And the basic idea here is all of these lines between the bumps should have a constant slope, because the fact that the acceleration is constant, for an inclined plane, generally speaking, we should see the velocity increase by the same amount as it decreases. It should be important to note, I think, that not only does that just make sense if you really deeply think about the setup, but also based on what they told you about the average velocity. The fact that the average velocity is going to always remain constant is basically going to mean that whatever amount the velocity decreases by when it hits the bump, it's got to increase by that amount once it gets to the other bump, right? Because the only possible way the average velocity would be constant is if it keeps fluctuating between these two values, back and forth and back and forth, the same max value and the same minimum value. Now, of course, because we should remember from kinematics here that when an object is accelerating, the average velocity is just literally the arithmetic average of the two velocities. That dotted v average line has got to be right in the middle. And so basically that should be horizontal. That was definitely trending upward there. Sorry about that. That should be labeled here v average. And it makes sense that it's going to be directly between these values because, the reason why the average velocity is constant is that it keeps fluctuating up, down, up, down, up, down. That's the point. Take a second to pause this video here and just take a look at this graph. Make sure you understand really what we're trying to get at with it. And when you hit play, take a look at the scoring guide. All right, so looking at the scoring guide here, we see a graph that's looking very similar to the one I just drew. Of course, these really are not going to be exactly vertical, which I kind of basically drew, but only by accident because it's very hard to draw with this digital pen. Notice here, you get 1 point for having a constant upward slope in each segment between bumps. That makes sense because the acceleration is g sine theta, again. You get 1 point for having a velocity reset abruptly at each bump. Notice it says, in other words, like a sawtooth function. Notice it looks like the teeth of a saw, not a sinusoidal curve, to a minimum positive value that is the same for each bump. Notice here, if we draw a horizontal line, you'll notice these are all at that same vertical value. And then notice it says 1 point for having the same maximum value in each cycle that occurs near the bump times. And it says this point can be earned for a sinusoidal curve with peaks at the bump times. It should be clear when a car crashes into a speed bump, it does abruptly slow it down. So it is going to be a sawtooth function and not a sine curve. A sine curve would show like a nice, uniform, gradual acceleration. The reason why it's a sawtooth function is because when it hits the bump, I mean, you can imagine if you've ever been in a car when you hit a speed bump, it's a big jerking motion that slows you down. That's why they're there, particularly on blocks where there are schools. And then our last point here, this was a 4-point graph, which is rather unusual for the AP test, but nonetheless. You got 1 point for drawing your V average line that is horizontal and consistent with the graph drawn, even if that graph is wrong. So to be clear, if you just really punted on this question and you just drew a line that looked like that, well, at least you got 1 point. Take a second to pause this video here and check out that scoring guide, making sure you understand all aspects of it. And when you hit play, we'll move on to part B. All right, moving on to part B here, it says, suppose the distance between the bumps is increased, but everything else stays the same. Is the maximum speed of the cart now greater than, less than, or the same as it was with the bumps closer together? Now, the answer here should not be much of a surprise. The answer here is going to be greater than. And you know what the first thing I thought of when I looked at this question was? The first thing I thought of was the tangerine question that we did on the free fall test. We talked about how objects having the same acceleration doesn't always mean they experience the same speed change, because if you take the acceleration equation, delta v over t, and you solve it for delta v, you get delta v is acceleration times time. The fact that the ramp is still angled at the same angle definitely means it's going to have the same acceleration. But if the bumps are farther apart now, the thing is going to be accelerating for more time. And if it's accelerating for more time, then the speed change is going to be bigger. This is what I wrote. If the bumps are spaced farther apart, the maximum speed reached by the cart will increase. The bumps serve to slow the cart down. So if the bumps are spaced farther apart, the cart will be able to travel more distance and thus spend more time traveling between the bumps. The change in the cart's velocity is determined by the product of the acceleration and the time spent accelerating. And then here's the big payoff. Since the baseball, what the heck is that doing there? That's obviously supposed to be the cart. When I was preparing for this yesterday, I must have been watching something about baseball. Since the cart, sorry about that, guys. Since the cart would be experiencing the same acceleration, but now for a longer period of time, it will reach a larger maximum speed. Take a second to pause this video here and write that down. Make sure you don't write down baseball. Sorry about this. I was preparing this at about 11 at night last night. And when you hit play, we'll move on to the scoring guide. All right, looking at the scoring guide here, we get 1 point for saying there's more time between the bumps and 1 point for connecting that the cart has more distance to accelerate between the bumps, has more time or more distance. Notice you can argue that in a number of ways, specifically because there are different kinematic equations that are going to describe how this object moves. So if we use the equation Vf equals At, then we can show here that the final speed is going to be bigger because it's proportional to the time, right? At a constant acceleration, more time means more final speed. That said, we can also say, well, the equation Vf squared equals V naught squared plus 2Ad would show the final speed is proportional to the square root of the distance. So more distance means a larger final speed also. Their example is the maximum speed is greater because the cart has more space, parentheses, or time to accelerate, parentheses, build up speed between the bumps. Now, I like when they put alternate solutions because they don't want to force you to think about the thing just one way. I am interested to see if any of you wrote this because I think it's kind of a weird approach, but notice it works just fine. 1 point for indicating that the potential energy difference increases due to increased height between the successive bumps, and then 1 point for relating the increase in potential energy to an increase in kinetic energy. The basic idea is if you're traveling from point A to point B on a ramp, you can measure the height using trig. It's going to be that height. But if it's going now further down the ramp, like let's say to point C, the height difference between those points is now bigger. And so it's going to lose more potential and thus gain more kinetic. An interesting way to think about it, I don't know that it's obvious. I did not think about it that way, to be perfectly frank. I thought of the tangerine argument. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. All right, moving on here to the next question. It says, with the bumps returned to their original spacing, the track is tilted to a greater ramp angle theta. Is the maximum speed of the cart greater than, less than, or the same as it was when the ramp angle was smaller? Well, I already pretty much talked about this one in great detail. The answer is going to be greater than. The net force acting on this object is FGX. And notice FGX is proportional to the sine of the angle, which grows when the angle gets larger. The sine of the angle is directly proportional to the angle. And so that means when the angle gets bigger, a larger component of gravity is going to be pulling this thing down the ramp. So of course the acceleration is going to get larger. Let's see if we talk about any baseballs here. If the angle at which the ramp was tilted was now larger, the maximum speed of the cart, yes, would be greater. If the ramp was tilted at a greater angle, the component of the block's weight acting down the ramp would be larger. This is possessive. There should be an apostrophe there. If the cart was experiencing a larger net force down the ramp, it would experience a larger acceleration. According to the time-independent equation, I went here. I thought that this made sense with the distance argument. According to the time-independent equation, if the distance between the bumps, the distance over which the cart is accelerating, is the same, but the acceleration is larger, then the final speed of the cart would be larger. No baseballs. Take a second to pause this video here, write that down, adding any parts of this explanation that may be missing from your own. And when you hit play, we'll jump to the scoring guide. All right, moving on to the scoring guide here, you can see you got 1 point for indicating the acceleration is greater and 1 point for indicating that the component of the gravitational force increases. I will sympathize with you if you're thinking it's kind of stupid the way they write these scoring guides because they want you to talk about kinematic equations in the first part. And so you would think, well, they want you to continue talking about kinematic equations. And then they just don't in this part at all. It's kind of weird. You make your argument as best you can. That's why I always think it's good to flesh these things out as much as you can, as quickly as possible. But that's that. Now, notice here, in a very similar style to the last question, if you have these two ramps, one of them tilted larger and one of them tilted shallower, let's just pretend that's a straight line. If the thing is tilted up at the same angle, the distance between two bumps that are equally spaced are now going to have a bigger height difference between them. Look how small that height difference is when it's not tilted much, whereas at the larger angle, the height difference is much more. So the basic idea is the potential energy difference is going to increase when you raise that angle up once again. And so to some degree, I think the elegant solution here is actually the energy solution because it's the same argument twice. You tilt the ramp, you're going to have more potential energy difference, so you're going to have more kinetic energy. Now, I don't think about it like that because I saw a ramp and I figured this is an inclined plane problem. They're talking about average speed. But it's important to realize the applicability of these types of argument styles that we've been talking about so far this year. You see a ramp, you should think two things: inclined plane stuff and energy stuff. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide. When you hit play, we'll move on. All right, here, last part. We've got two parts to this last little part here, part D. It says, before deriving an equation for a quantity such as V average, it can be useful to come up with an equation that is intuitively expected to be true. That way, the derivation can be checked later to see if it makes sense physically. A student comes up with the following equation for the cart's maximum average speed. The equation is V average equals C mg sine theta over d, where C is a positive constant. Now, this was the year of the controversy with the positive constant, and that's why they write now, after that, with appropriate units. So this is the only time I think you're ever going to see that again without the phrase with appropriate units, because they realized they messed up. Part 1 here says to test the equation, the student rolls a cart down the long track with speed bumps many times in front of a motion detector. The student varies the mass of the cart with each trial but keeps everything else the same. The graph shown below is the student's plot of the data for V average as a function of the mass. And it says here, are these data consistent with the student's equation? Briefly explain your reasoning. I think a lot of you looked at this question and thought, oh my God, they asked something that easy on the AP test? Geez. Fortunately here, they did you dirty. The answer is no. You got to make sure you're really understanding what they mean when they say a linear relationship. Let's talk about what you thought, then let's talk about what the graph shows. I'm going to go ahead and assume that almost all of you here said yes. And you said, looking at that equation, the average speed is directly proportional to the mass. Looking at this graph, that's a line. So of course, they're directly proportional. They're not, though. Yes, this graph is roughly in the shape of a line, but it is not showing a direct relationship like the equation shows. Well, how would you possibly know that, you might ask? Well, let's think about the 1-1-1 rule. The 1-1-1 rule shows that if the mass of this object doubles, then what we would expect to see is a doubling of the average velocity. Okay. Yeah, that makes sense, right? If you just plug in the 2, you're going to pull the 2 to the outside and just get it's twice the average speed. So if your mass is 1 and the velocity is, I don't know, let's call that 1.3 or something, then when the mass is 2, we should see a velocity like 2.6, and it's just barely over 2. That's the problem. While it does show as the mass increases, the average velocity increases, it is not increasing in the way that is suggested by the equation. That's a really important thing to realize here. When variables are truly directly proportional like this, a 1-to-1 relationship, it's in the numerator, it's not squared, there are no other numbers attached to it. When that mass doubles, the average velocity should double, and this graph is not showing that. The answer should be these data are not consistent with the student's equation. According to the student's equation, the average velocity of the cart is directly proportional to the mass of the cart. The graph does not show a linear relationship, so the equation isn't consistent with the data. If the graph showed a mass, which was directly proportional to the average velocity, when the mass is doubled, the average velocity would double, which isn't the case for this graph. Now, the reason why I showed you this question right here, right now, is to teach you this. This is really important. It is an easy question to answer correctly, and it is a super easy question to answer incorrectly. You want to make sure you're really being careful with that, because if you answered yes and you said, well, the thing is directly proportional, blah, 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 whatever. You said what you know, what I've been training you to do all year. You totally had the right idea. You're doing a physics. The only problem is they screwed you with this janky graph that they intentionally made to look straight. So please be careful with that. Let's take a jump to the scoring guide here. Notice the scoring guide says you got 1 point for indicating that the average velocity is not proportional to m, and then 1 point for connecting the equation to the data. They said here you could say the y-intercept of the graph is not 0, but the equation indicates that it should be. I think that's a weird way to think about it. The second option says doubling the mass from the graph does not double the average velocity, but the equation indicates that it should double. I think that makes sense. If you selected yes, you could at least earn half the points for indicating that they look approximately proportional, or for explaining that V average increases with M. So they screwed you up a little bit, but at least they give you half the credit for the trouble. Keep in mind, 50% is what you need to pass. You all should know what a directly proportional relationship is. I know I don't let anybody leave my honors physics class without being able to answer that in their sleep. As one increases, the other increases. The AP Physics little adjustment that we need to make to it is when one increases, the other increases in proportion. One doubles, the other doubles. One triples, the other triples. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. And the last part of this question here says another student suggests that whether or not the data above are consistent with the equation could be incorrect for other reasons. Does the equation make physical sense? Now, the answer here is no. I'm going to rewrite the equation right here. Honestly, I was mad after this year. And my students did fine. I was going to say this was the days of the test before any of my students had ever gotten a 5. This was only on the second year the test ever existed. I think the first kid to get a 5 came the next year. But the kids came into that classroom the next day and they were so proud. They were like, yo, mister, you would have been so happy what we said on this freaking test. They gave us this equation. They said this thing had a constant. We looked at the rest of the equation. We said mg has units of newtons. D has units of meters. And so newtons per meter, that's the unit for the spring constant. That's not a unit for the average speed. They didn't give them anything for that. They said, well, C could have constants to make it work, or it could have units to make it work out to units of meters per second. Notice this was the controversy why they always say that now. This was bogus. Look at the actual structure of the equation. It says the average speed is proportional to the mass. Now, that doesn't necessarily totally make sense in and of itself, but notice the top there is mg sine theta, which would suggest as fgx gets bigger, the average speed is going to get bigger, and that makes sense. But it also says the average speed is inversely proportional to the distance between the bumps, meaning as the bumps get farther and farther apart, the average speed is going to go down. Well, if the bumps get infinitely far apart, right, or as they get closer to being infinitely far apart, then it's just a ramp where the acceleration is just going to be g sine theta. So that doesn't make any sense. So that's the part of this that's wrong. No, the equation could not be correct. As we answered in a previous part of the question, when the distance between the bumps increases, the maximum velocity and thus the average velocity should increase. However, according to the equation, the distance between the bumps is inversely proportional to the average speed. Since we determined a larger distance produces a larger average speed, that means the equation should show them being directly proportional and not inversely proportional. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at the scoring guide. All right, moving on to the scoring guide here, we've got 2 points. 1 point for indicating that the distance dependency is not correct, and 1 point for indicating that in the equation, a greater D leads to a smaller average V, or for stating or implying the contradiction between this inverse relation and the reasoning in part B. So basically, they just wanted you to say it's inversely proportional and then say what that means. That's the idea. And so their example says, according to the equation, a larger distance leads to a smaller average speed because they're inversely proportional. But according to the reasoning of part B, a bigger distance between the bumps leads to a larger maximum average speed, showing that the equation is implausible. They actually also, I thought here, even though this question was like a big screw job, they did say here, if yes is selected, 1 point can be earned for indicating that an increase in the angle increases V average, which is true, as we answered. I guess that was part C. And so notice there was a lot of stuff you could have got wrong on this question that they gave you half credit for. And listen, I understand that's not ideal. I'm not suggesting that. Let's be clear about that. But it's important to realize on the free response, your goal is to scrape up as many points as you can. And if you take an L on a question like this and just get 50%, first of all, you need 40% to pass. So you're still ahead of the game. But there's going to be questions that you just destroy. Like, that's important to realize. We've been looking at harder questions from tests. So, of course, they're difficult. You're probably just forgetting that there are a lot of questions that are easy. Keep that in mind. Take a second to pause this. Make sure you understand the scoring guide when you hit play. We'll move on to part 2. All right, next question. One of the weirder questions I've ever seen on the AP test. I think it's interesting. It says identical blocks 1 and 2 are placed on horizontal surface at points A and E, respectively, as shown. The surface is frictionless except for the region between points C and D, where the surface is rough. Beginning at time TA, block 1 is pushed with a constant horizontal force. Notice they underlined constant for you. Oh my God, what a gift. Between point A and B by a mechanical plunger. Then it says upon reaching point B, it loses contact with the plunger and continues moving to the right along the horizontal surface toward block 2. Block 1 collides with and sticks to block 2 at point E, after which the 2-block system continues moving across the surface, eventually passing point F. What they want to know is what the graph of the speed of the center of mass of the 2-block system looks like as a function of time from time A to time F. The time at which block 1 reaches point A through F are indicated on the axis. Now, there are a couple of things that can be said about this question. I panicked when I saw that this was a question on the AP test because I said, oh my God, we really rushed through center of mass. We don't really say a lot about it. Oh my God, now there's a whole center of mass question on the AP exam. Go back to basics. I have up to this point expected you to remember basically one thing about the center of mass, and that is that the momentum of the center of mass is conserved in the absence of external forces. So, if the momentum of the center of mass is conserved, that means the speed of the center of mass has to be constant, and if there's a force, then the force is going to change the speed. It says in the problem from A to B, this plunger is pushing with a constant horizontal force. Notice that makes this different from a spring where like the force would be decreasing over time. And so instead of the gain in velocity sort of like tapering off like that because the acceleration is getting smaller and smaller, it's a constant force. That means it's a constant acceleration between A and B. Let's just draw a constant acceleration here between A and B. You're going to have to excuse me if these lines are not straight here because it's super difficult to do this with the digital pen. Oh, not bad. Okay. So we have an increase in the center of mass of the system because there is an external force exerted on the system. If the system has no external forces exerted on it, its momentum is conserved, meaning the speed of the center of mass remains the same. But in the absence of external forces, it remains constant. Where's that friction section? The friction section is at point C. So notice here between B and C, there's no external force exerted on this thing. That means between B and C, the velocity of the center of mass is going to remain constant. So we're already seeing this graph take shape a little bit. An external force from A to B causes an increase in the speed of the center of mass, and no external force between B and C causes it to remain constant. Now from C to D, we can see that friction section. And so that's going to slow the object down, but it's still going to move to the right afterward. So it's going to slow it down, but it's not going to slow it down completely. So let's just have it like come down to there or something. And we'll say here that the line is going to look something like this, maybe. And it's supposed to be straight. And that's that. Notice the velocity of the center of mass decreased because it had a force acting on it in the opposite direction of the velocity of the center of mass. So we had a force in the direction of the center of mass and it sped up. Now we have a force in the opposite direction of the center of mass, so it slows down. All right, now we have between D and E, and D and E, there's no friction again, and it hasn't touched block 2. So between D and E, we're going to have a constant velocity again. And now at time E, it crashes into block 2, and it sticks to block 2. Who cares? Block 2 is part of the 2-block system. In the absence of external forces, the the momentum, and thus the speed of the center of mass of a system remains the same. And that's it. That's the graph. There's nothing more to it. Take a second to pause this video here and write that down, making sure you make any corrections to your graph or any notes here. We'll actually take a moment to write some notes here. We'll say the force increases the CM's, center of masses, momentum. And then we'll say here the friction force decreases the center of masses momentum. Take a second to pause this video here and write that down. When you hit play, we'll take a look at the scoring guide. All right, looking at the scoring guide here, there were a lot of parts in this graph. Notice there are 5 points here. First point is for a straight line that begins at 0 at TA and increases between TA and TB. Piece of cake. Increases. That's it. Notice it doesn't even say how it increases. It just says it increases. That's super generous. You drew an exponential growth curve. That's dead wrong. They said the force is constant. They're still giving you the point. 1 point for a segment that is horizontal and non-zero between TB and TC. 1 point for a segment that decreases linearly between TC and TD. Now, they did want you to draw the linear decrease from the constant force of friction. You got 1 point for a segment that is horizontal, non-zero, and constant, but at some different value than the higher horizontal portion of the graph here, between TD and TF. And then you got 1 point for a curve that is continuous the whole time, with the possible exception of TE. If the speed changes at TE, the 4th point is not earned, while this point may still be earned. If you drew a horizontal line along the time axis because you just had no clue, they gave you nothing. I'm going to go ahead and assume that's not any of you. Take a second to pause this video here and make sure you take a good long look at this scoring guide. Figure out what you earned. Figure out if you have any questions for me. And when you hit play, we'll move on. All right, moving on to the last part of this question here, which is the last part of this video. It says the plunger is now returned to its original position and both blocks are removed. A uniform solid sphere is placed at point A as shown. The sphere is pushed by the plunger from point A to point B with a constant horizontal force that is directed towards the sphere's center of mass. The sphere loses contact with the plunger at point B and continues moving across the horizontal surface toward point E. In which time intervals, if any, does the sphere's angular momentum about its center of mass change? First question's gotta be, how do you change the angular momentum of an object? The answer is pretty simple. You apply a torque. Remember, the equation in the reference table says torque is equal to the time rate of change of angular momentum. I actually think it's solved for delta L. So it says torque times time. You got no torque? Then you have no change in angular momentum. They give you like a really super important hint here that they not only tell you the force is constant again, but they tell you the force here is directed toward the sphere's center of mass. That means if we took a look at drawing the position vector from the pivot point to the point of application of the force, they're parallel. There's no change in the angular acceleration from A to B. Notice from B to C, this is just a frictionless surface. That doesn't work either. From C to D, there is a frictional force, and hopefully you remember from the ramp problem yesterday, if we have a friction force and we have a position vector drawn from the center of mass to the edge, that force is going to cause a torque. That's where it's going to start rolling and not slipping. And then, of course, it's going to keep that angular momentum because the angular momentum is conserved in the absence of external torques. And since there are no external torques thereafter, that's it. Let's move on to an explanation here. Briefly explain your reasoning. I wrote, in order for the sphere's angular velocity to change, there must be a torque acting on it, since the torque is defined as the time rate of change of angular momentum. Since the problem says the plunger exerts a force that is directed towards the center of mass of the ball, it doesn't produce a torque, which means the angular momentum of the ball doesn't change. As the ball rolls between A and C, there is no other external force that will cause the ball to experience torque, and thus a change in the angular acceleration. However, from C to D, the force of friction acts some distance away from the pivot point, which produces a torque and thus causes a change in the angular momentum. Take a second to pause this video here. Make sure to write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, take a look at the scoring guide. All right, moving on to the scoring guide here, we see that they gave you 1 point for reasoning that a change in angular momentum is caused by a net external torque. So even if you just had no clue which segment that actually happened in, if you said that, they gave you a point. And then you got 1 point here for correctly indicating that the friction from C to D is the only force that produces that external torque over the entire time interval. Notice it says this point is not earned if a statement is made that the angular momentum or angular speed decreases between C and D, or that the sphere stops rotating at point D. Now, it says here, the claim, evidence, and reasoning chain here is the sphere's angular momentum about its center of mass changes in the interval CD. There is friction between points C and D, and then friction applies a torque in the region C to D about the central axis of the cylinder to change its angular momentum. Now, notice here, and this is the part that is a little tricky, it wasn't rotating. Now it is once it hits that patch. Its angular momentum actually increases. That's the only part of this that I think might be a little confusing. But notice here, if this thing is sliding along, this frictional force is going to cause this thing to start rotating from this perspective clockwise. The angular momentum over here, though, is 0. After that friction segment, the angular momentum is greater than 0. That friction section actually causes the ball to start rolling. Crucial piece of information. Take a second to pause this video here. Write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. All right, everybody, that is it for today. I hope you liked these questions, found them to be interesting. They are a bit unorthodox, a bit confusing, a bit weird, but I think they are totally worth our discussion and examination. And I hope you learned something from doing them. Tomorrow, we're going to be able to take a good, close look at some stuff you'll need to talk about for lab. Have a good one, everybody.